Okay, good afternoon. So today's lecture is about combinational circuits from Boolean algebra to gates, and I hope you saw a little bit of Boolean algebra in the recitation yesterday. So just to recapture the organization of the course, we have actually finished the first module of the course, which was about assembly language programming. And now we are entering the second module, which is all about logic design. You will be learning a lot about logic design in next 8 lectures. And the interesting thing is that, I can list all these topics like combinational circuits and sequential circuits. Most important thing you'll be learning is how to express these things in another language called BlueSpec. And all the labs from now on will be done in BlueSpec. So that's why you have to really understand it in detail. And then another very important concept, which is logic synthesis, that whatever we write at high level, how does it get translated into actual hardware, into actual gates that are fabricated. And it turns out there is a fair amount of sophistication in that, and you will understand up to what extent you have control over it, and beyond that you rely on tools and somebody else doing their job in this. And after this module, the interesting thing is that both these first and second modules, so these two modules are independent. We could have done them in any order. But the third module, which is the implementation of RISC-V processors, we could not have done without doing both of these modules. So don't think that the assembly language programming you have learned is going to go to waste. It's extremely important, right? Because we're going to design general purpose processors starting module 3. And after that, we will after doing quite a few implementations, we'll move up again and see what additional software demands are there, which come up in the form of operating system, because you never buy a machine naked. You always buy a machine with some lot of resident hardware, a lot of resident software on it, right? And in the end, we'll look at some multi-core issues. All right, so with that background, let's start with combinational circuits. And combinational circuits have binary inputs and binary outputs, right? Ones and zeros, that's what we are talking about. And the interesting thing about them is they're always a function. They're always a function. So in this case, there are 3 inputs. I'm showing bool cross bool cross bool, and it produces 2 outputs. So it's bool cross bool as the output of this. And any Boolean circuit that you can write, is interesting, and it's a very, very powerful idea, the system. But you should not lose track of the fact that these things, there are 2 different worlds out there. One is simply the world of Boolean algebra, Boolean functions, which stand on their own rights, regardless of how we implement them. And you'll find very, very wide uses of it. And the second part is, how do we realize them in hardware? So from today's lecture, we'll start getting into the basics of it. How do we take something, some circuit, some idea in a Boolean circuit at a high level, some Boolean expression in a high level, and how do I express it? How do I generate actual hardware that will accomplish the same function? Another way to think about Boolean circuits is that they have no memory. So if you give it the same input, you're always going to get the same output from it. It doesn't remember anything internally. And that's also a very interesting thing, because pretty soon we will transition to sequential circuits, which is all about state, state embodied inside the circuit. And both the abstractions are very important, but they come in this order. First you have to understand combinational circuits, and then we'll get into sequential circuits. Okay, so let's start with something which you may have already seen in your recitations, but if you have not, it's very straightforward. So there's a truth table here which describes the function of NOT, or an inverter, right? That you give it a 0, it produces a 1. You give it a 1, it produces a 0. In hardware terms, it's, this will not show. In hardware term, we draw an inverter often in this form, right? So it produces the opposite of S. And I'm not very good in drawing over bars, over thing in PowerPoint is limited, so I'm going to use this tilde, which is okay, right? So you can use that to describe that's a not of A over there. Okay, other very important gate is the AND gate, and the definition of AND gate simply is that both the inputs have to be 1 before it can produce a 1. If any input is 0, it automatically produces a 0 in it. So that's what this truth table captures, and you see the symbol for an AND gate given here, and we will often write in Boolean expression AND gate as a dot. Right? So these are all completely equivalent representations in this. And the third very important gate is OR, and as the name implies, it produces a 1 if any of the inputs is OR. So it produces a 0 only when both the inputs are zeros in it, and that's what is again captured by the truth table. You see the symbol, and we often write OR as a plus operator, so A plus B. So just as, and it has very, very similar properties to the plus on integers and so on, but some properties will be different. Okay, and you have already seen the Boolean algebra axioms for it, so I won't repeat it over here. Let me just continue with gates. So there are some other gates which are very famous, and you will hear about them. So one of such gates is NAND, and as the name implies, it's and not together. NAND, not and, right? And all I did was I took the output of this gate and inverted it. So it produces 1, 1, 1, 0, which is the exact opposite of AND, which produced a 1 when both the inputs were 1 in it, right? So this, this is the definition of it, and there is no special symbol for it in Boolean expressions. We just write not of A dot B in this. And other interesting gate is a NOR gate, which is NOR, not OR. So I took the output of the OR circuit and inverted it. So you see that it produces a 1 only when both the inputs are 0, 0. Otherwise it always produces a 0 on the output. And again, no special symbol at the Boolean expression level, but in pictures we'll often draw this NOR gate with a tiny, circle at the output of it. Now, the interesting thing about these things is the functionality of these gates can be expressed using NOT and NOR gates, right? It's obvious that I could have written that NOR gate simply, somebody may think it's just a shorthand. You don't want to draw such a big picture, so you turn it into a small circle and attach to it. It's not a bad way of thinking about it, but mathematically what we are saying is that a NAND gate can be expressed using an AND gate and a NOT gate. Similarly, NOR gate can be expressed using OR circuit plus, combine it with inverter, combine it with NOT operator. Okay, so one more gate, which is so famous that it has actually a special symbol in representation Boolean expressions, and you see that symbol being used here, A, this thing B, and exclusive OR, as perhaps the name implies, produces a 1 only if one of the inputs is 1. If both the inputs become 1, then it produces a 0. So that's why it's called exclusive OR, that everything can't be 1, only one of the inputs has to be 1 in this case for exclusive OR to do its job. And like NAND and NOR gates, exclusive OR gate can also be represented using other gates. So you can express it using these gates. Why? Because if you look at the Boolean expression for it, under what conditions does it produce a 1? A has to be 0 and B has to be 1, or A has to be 1 and B has to be 0, and that's what is captured by this a Boolean expression over here, not A dot B or A and not B. And this is the definition of exclusive OR. So you're doing several things simultaneously. I'm giving you the definition, but it's also telling you that whatever this gate is expressible in terms of other and or and not gate. And at this time you might be wondering, if everything is expressible using and, or, and not, why are you telling me about these other gates? And you will get answer to that in spades in the next lecture. Because when it comes to hardware implementation, we may have a preferred form. We prefer some gates over other gates. So we'll discuss that in the next lecture, but today I'm just showing you, yes, these are gates, and there is another very interesting property that I wanted to discuss of this. This is just a slide on nomenclature, that if you don't get confused by different words we'll be using. So for example, combinational circuits, Boolean expressions, Boolean circuits, these are all with the same equivalence class. Given my mood and the temperature, we use different things, right? Whatever I can remember. Or things like gate or a Boolean operator, they're also synonymous in our thinking. So this is just very, very standard nomenclature. Everybody does that. Now, what is the role of variables? So this you have to get used to, because this is somewhat different than what you have seen in software languages. Here a variable is always going to be name of a wire, right? So there is a wire called A in my circuit. There is a wire called B in my circuit. So whenever I use names, it's always, I'm trying to name some wire in my circuit, okay? Truth tables. Truth tables. We already saw baby truth tables, for all these operators I showed you. But in general, if I have to write down a Boolean function, f from a, b, c, which produces s1 and s2, I can always describe this using a truth table. And truth table simply is, tell me all the inputs, and for each input, you have to give me an answer. You have to specify the value of S1 and S2 for each combination of A, B, and C bits that you're getting. And the best way preferred way of writing it down is like this, that you have, if A, B, and C are 0, 0, 0, then S1 is 1 and S2 is 0. It's simply an enumeration, right, of all the possible inputs, and for each input you are specifying what is the output. And this circuit seems to have, happens to have two outputs, S1 and S2, so you have to describe one column for each one of them. Output for S1 and the output for S2. Okay, so first question, what is the size of this truth table? Right? Suppose you have n inputs. How many rows this truth table is going to have? 2 to the n, right? It's exponential, right, in number of bits. So it's a little bit daunting to think what will it be like if you had 32 inputs, or if you had 64 inputs. So that's something to think about. And of course you have to use one bit to describe every output. All right, so essentially a truth table is going to contain 2 to the n rows of 2 bits each, or m bits each if m is the number of outputs you have got in your circuit. Now it should be obvious to you that this is not practical. I mean, we can't define very big circuits. We can't define circuits with lots of inputs in this manner, because we'll run out of paper. I mean, it may not even fit in a computer, such a truth table description. Yes, please.
On the slides, there's an n plus n inside.
Yes, I saw that. Sorry, I made that correction. So you don't have to record the input, right? Because that's implicit. You're given a bit pattern, you just use it as an index. You go and read that element in the table. So table should not have, You don't have to record it unless it's a sparse truth table or something, then you will have to record it. Good question. Any other clarifications about this? Now, so what I have shown you so far is any combinational function can be described using a truth table. It sounds very reasonable. I mean, it's like describing a map, a function. You give me all the inputs, tell me what is the output corresponding to each input, right? So as long as your domains are finite, this works fine. But now I want to go backwards. Given a truth table, can you actually immediately realize it in terms of gates? Can you tell me what will be the Boolean expression corresponding to this truth table? And the Boolean expression corresponding to this truth table is not unique by any means, but let me give you one that can be derived very easily. And the way we do it is we look at every place where there is a 1 in the output, right? So what is the first one you find here? It's in the line 0, 0, 0, right? S1 is 1. So if I have to write S1, I write a product term for every row where S1 was 1. Make sense? Right? So you have 0, 0, 0, which is not A, not B, not C. And then the next one is in 1, 0, 0, which is A, not B, not C. And the third one is 1, 0, 1, which is A, not B, and C. You sum them all up and you have a representation. This is clearly a Boolean expression. So I'm giving you a mechanical way. If you gave me a truth table, I can certainly produce a Boolean expression corresponding to it. You could have done the same thing with S2. Now, such representations are called sum of products, because each term is a product term and you're just taking a sum of it. Some people also like to think of it as a two-level representation, right? You first form the product terms and then you add them all together and then you have the circuit, for doing it. Has everybody understood the method of doing this, right? We examine the truth table. Wherever we find 1 in the output, we go and write a product term corresponding to it. And if we have collected all such product term, we have a description. We have the Boolean expression corresponding to this truth table. Okay. The other idea which is very interesting is this notion of universal gates. So you can have a set of gates using which you can express anything, right? And you have already seen and, or, and not form a universal set. How will you prove such a thing? See, proof is, we have already given it, right? Because we are claiming you can write any Boolean function using truth tables, and I have already shown you how to take a truth table and transform it into sum of product expression using ands, ors, and nots. So if I can do that, then clearly I can take any Boolean function and write it only using and, or, and not in it. Very interesting. The second one may not be so obvious. It turns out NAND by itself is a universal gate. I can express all Boolean expressions using NAND. See, really? That sounds strange, right? In fact, you can express all Boolean functions using just NOR gate. So each of these gates by itself is a universal gate. It can express any Boolean function. How will you prove it? So here is a pictorial proof. You see, we already know that not, and or are universal. So if I can give you a realization of a not in terms of NAND gates, and if I can give you realization of all these 3 gates in terms of NAND gates, we are done. All right, so here is my picture. Just focus on the left column in this. So does this NAND gate capture the truth table of not? Yes? Just work it out. What is the what will happen if you gave it a 0? What is the AND of 0, 0? 0. And what is the NOT of that? 1. It behaves like an inverter. And here these proofs are actually complete, because all you have to do is try it on 0 and 1, and that's it. Because our domain consists of only two numbers, here 0 and 1. And here is the second one. Here is an expression showing the equivalence of that a NAND gate, AND gate can be expressed using a pair of NANDs, and an OR gate can be expressed using this combination. In every case, whenever in doubt, just draw the truth table for both sides and you will see what answers you can get. It's not so many things to look at, because we're talking of two input things, so there are only 4 cases to compute, and you will find it equivalent. And the right hand side is the proof that NOR gate is universal, because using NOR gate also I can express AND, OR, as well as NOT. So does everybody get the idea of a universal gate? We have already come to believe that AND, OR, and NOT form a universal set, and if I can express those 3 gates using some other gates, then that will form a universal set. And I'm showing you how to express AND, OR, and NOT using just NAND or just NOR. So that completes the proof, that these are universal gates. Okay, so now, this is why we are here. We want to build some hardware to do interesting things, and we're going to start with very simple things. So let's just have a quick review of binary addition. But before that, let's review decimal addition. Can everybody add 14 and 7? So we add 4 and 7, and what do we get? Carry of 1, and then we add 1 to 1, and then we get 2. And binary addition is no different. You just express the number in binary form, right? Convert each number to the binary form, and the addition will be performed the same way. So when I add 0 and 1, what do I get? 1, carry of 0, right? And when I add 1 and 1, what do I get? 0 and carry of? Very good. Now what? 1, 1, 1. So now I will get 1 as the output and carry of 1. And now when we're done at this point. Okay? I'm sure you can do binary addition. But what I'm interested in is, can we build hardware, right? So let's build hardware to do binary addition. It's fun. You'll see it. You have to start somewhere, before we start building these fast computers which can execute any program. Let's start with let's see if we can build an adder. So even full adder was taking 3 things. It was taking 2 bits and a carry bit. Let's solve a simpler problem, which is called half adder. Half adder is just give me 2 bits and tell me what is the sum bit and the carry bit. Okay, so it doesn't take very long to figure out that this should be the truth table for half adder, that in order to produce a 1, at least one of the bits must be 1 in it, and if both the bits are 1, then the sum bit becomes 0, but the carry bit becomes 1 in this. So this is the description of it, definition of it. All right, and I just wrote it down, copied from left to right. I can immediately derive the expressions in Boolean expressions corresponding to this truth table. So this is my definition of half adder. Very good. Now we are trying to build a bigger and bigger adder. So let's try to build a full adder now. So full adder is doing what? It's adding 2 bits, and then whatever results you get, it adds the carry bit to it. All right, so when you do that, you will see that I need 2 half adders. So first half adder is performing something and producing a sum bit and a carry bit, and I take the carry bit from the first half adder, add it to the second one, and then I get the sum bit coming out of it. And if either of them produced a carry out, then you will have a carry out going out in the full adder case. So you can derive this, right? You can just, if you understand how half an adder works, you should be able to combine it in this manner and say, yeah, this seems to do the full adder job, the kind we saw on the previous slide. At least that's the functionality we are trying to achieve in our minds. All right, so I'm going to redraw this in this fashion. So I have two inputs coming in, A and B, and there is a carry in and a carry out, and sum is the result. Sum bit is the result. So it's a 3 input, 2 output circuit, but drawing it in this fashion is just, you'll see a reason in a second. Okay, so there is no difference between the left and the right hand circuit here. I've just redrawn it. Okay. Now I want to build a full adder, right? So 4-bit adder I have to build. So if I want to build a 4-bit adder, I can just cascade these things. Right? The carry that came out of the first full adder, I feed it to the next full adder. Carry from it, I feed it to the next full adder. This is exactly what you were doing in your algorithm, right? You say carry, okay, next one, next one. At every stage you were doing a full adder job in this, and that's what's happening here. So that's the high level idea. Okay. But we want to describe a 32-bit adder, maybe even a bigger one. Would you like to draw a picture for it? How about truth table? This is not feasible, right? Writing a truth table with 264 rows is a tall order. Right? It may be ecologically also not sound to try to write a truth table of that sort, right? And it produces an answer and a carry bit, so that's why you have 32 plus 1 bits coming out of it. Okay, so what is the alternative? Well, I can write down the Boolean equations, right? I already kind of did on the previous slide. So you say, look, it's much, much shorter for me to write down. Instead of 2 to the 64 rows, let me just write down, 32 equations, where this equation feeds this equation feeds this one, and so on. So you will have, assuming each set has 3 equations or something, you will have 72 lines of code or less than 100 lines of code. Not a big deal. You can write down. But, as a computer scientist, you say, man, this sucks. I'm doing the same thing over and over again, and you're making me write straight line code for this. This is not so cool, right? So we'll see that. We'll discuss that issue. Is there a better notation than this? But any notation that can describe recurrences is suitable in some sense, and mathematician would have just written like that. He will write down the equation, say k ranges over this to this. Okay, circuit diagram we have already agreed is just too tedious. You wouldn't like that as a homework if I ask you to draw a circuit diagram for ands and ors corresponding to 32-bit circuit. All right. There is a deeper problem with these descriptions. Not only from my notation I want to generate hardware, these gates, but I also want to simulate it. Right? Because, there might be a mistake in my circuit. How do I know it's a mistake? I give it some numbers, it produces an answer, I'm saying, oops, that's not what I was looking for. Right? Mistake. In order to do that, I have to simulate. I have to give computational meaning to these boxes and say, oh, really, and behaves like this or behaves like this. So if you give me these inputs, this must be the output. Because at the end of the day, everything is a function. Everything is a Boolean function. So ability to simulate, ability to execute this program of whatever description you have, so that you give it some input, it produces some outputs, is essential regardless of what the purpose is for the notation. Because the purpose here is not to just learn the answer, the purpose here is to generate circuits. But even when the purpose is to generate circuits, ability to simulate the circuit is extremely important. And the moment we want, given the input, some output, what do you think of? Programming, right? We need some formal language, we need some syntax, we need some way of describing it so that it can be done. And in this class, we will be using BlueSpec system Verilog, sometimes called BSV, we in this course call it BlueSpec, right? Language, which is a hardware description language, to actually describe circuits and to be able to simulate them and see the answers, etc. Okay, so now let me write this half adder in BlueSpec. And we want to generate this circuit, from it ultimately. So by now you all know functions. So I write a function which is half adder, named half adder. It has two formal parameters, A and B, and the definition of S is, what is this funny sign, right? So this is the BlueSpec notation for exclusive OR. Whenever you have exclusive OR, you can use this caret over there. And what do you think the next one is? And, reads like and, right? Is this easy to write, this description? And what do you return, by the way? You're returning the carry and the sum bit you have computed, right? So you have defined the C, you have defined S, and now you're returning S and sum from it. Can everybody follow this program? It's almost encoding of the circuit, right? It's telling you this is connected to that, because remember, variables are always wires here in this. Now, it turns out it's almost there. It's not quite correct. We have to make some changes to make it really acceptable, right? And this is again maybe a new concept for some of you who have only seen Python. You're seeing a language now, BlueSpec, where everything is going to be typed, strongly typed. You have to declare, you have to say, this thing is 2 bits, this thing is 5 bits, this thing is 17 bits, right? And compiler will check, it won't let you cheat, so if you do wrong things, it'll come back and say, no, you can't do, you have to have the right number of bits in everything. So now I'm going to write down the types of everything. Very first thing, bit 2. It's saying function FA returns a result which is 2 bits. What else it's telling me? It's saying A is, argument A is 1 bit. Argument B is 1 bit. Yes? Now, how big is S? S is going to be 1 bit, so I have declared it. I have said bit 1, S is 1 bit and C is 1 bit, and the result 2 bits, right? Because we want to return both of those things in the result. And now whatever we wrote earlier is fine. It's just that I have to type declaration that says S is 1 bit wide, right? Says that result is a 2 bit wide quantity, right? 2 bit wide vector. And this is the thing you have to understand now. So remember, result has 2 bits in it, and we are saying the 0th bit is the same as S. This is specifying wiring, right? Because S is the name of a wire. Some circuit is hanging off to it. Its output is called S. And now I'm saying whatever result 0 is, it's also called S. Right? So that's what it does. And similarly, result 1. Okay, so once we have done that, this program has become legit. Now it has all kinds of type declarations in it. And some of you are saying, man, this really sucks. You know, you started out with 4 lines and you have ended up with 10 lines of code, right? This type declaration, I'm not buying it. There is lots of syntactic sugar available to make your life easier. And the advantage of having types, you will just come to appreciate them. You know, it may be like brushing your teeth at night, right? You may not see the value, but eventually you do see it, right? So I think you will see that how much headaches it saves you when you write types properly. So here is a slightly more convenient syntax. What did I change? So a type declaration and the definition of a variable can be written together. So I had written this in 2 lines. I said, oh, bit to A, and then I said A is this and this. Yes?
Given that this is so much like C, why aren't we just doing this in C, like its own library? Like, why do they need a whole separate library?
Very good question. So what is the purpose of C?
Well, C is like a assembler, but a little higher level thing.
Yes, but its role in life is to compute, right? You write something and gives answers. What is the goal of BlueSpec?
To simulate circuits. But that
No, not it's to generate circuits.
I see.
Simulation is a byproduct, very convenient thing, you know. So I can also simulate. So think of BlueSpec to the first order. This is a very imperfect analogy, as if you have PowerPoint, right? You need a language for drawing pictures, right? So that's what these circuits are. But unlike PowerPoint, here our pictures are very meaningful. So we can simulate. We can say, tell me, if I give it this input, what is the output? That aspect resembles C. That aspect resembles Python. That aspect resembles any language you have seen so far. But the reason we are teaching a different language is because its purpose is completely different. Its purpose is to generate circuits. And that actually raises another very interesting question. Why not generate circuits from C? And believe, many people have tried that. It's a very difficult thing to do, and you get all kinds of nonsensical circuits. So if you're trying to generate hardware, you need a model of hardware in your head. You need to know what is the purpose of the program. What does it mean to generate efficient hardware? So all those questions are the central subject here. That's what we'll be focusing on. Okay, the other syntactic convenience is this. You have already seen this syntax, these curly braces, which is like concatenation, which is the easiest way of writing a bit vector without assigning to bit 0, bit 1. Just write it there and put curly brackets around it. So if I do that, then this quantity has to be 2 bits. Why? Because C is 1 bit and S is 1 bit. So therefore this must be 2 bits wide bit vector. And by using bit vectors, by using curly notation, you will avoid having to write many temporary variables, right? So these things are extremely convenient. I mean, actually the language will become a real pain to program in if you did not have some of these things in it. Okay, so now we have graduated from half adder and we're going to write the full adder. I had already shown you the picture for the full adder in this. And so full adder has 3 inputs. Each one of them is 1 bit wide. I have A, B, and carry in. How many bits does it produce? Full adder? 2 bits, right? 1 sum bit and 1 carry out, right? What will be connected to the next stage in this. And let's see if we can write it, right? So I've named this function full adder. And now I say I'm invoking half adder on parameters A and B. And how big is the output of half adder? 2 bits, right? So AB is a 2-bit quantity. And what do I feed in the second half adder? One of the arguments is going to be C in, but what is the other argument? Whatever carry you got from the first place. And that is what is shown here, and you write it, and you know description is given here, which is very, very close to the picture that is drawn above it. Now, notice here that we have lots of things. So when I write AB of 0, what do I mean? How big is AB? 2 bits, right? So it has a 0th bit and a first bit. What was assigned to the 0th bit? You'll have to go and look at the definition of half adder, but it was the 0th bit was the sum bit, and the first bit was the carry bit in it. So I have taken this and put it in here. I'm adding it over here, extracts the carry bit from it, adds it, sees the OR of these two things to produce carry out, and now we are all set. The output is C out, as well as I have to return the ABC 0 bit from it. There are several things worth noting about this, and the most important thing is, in writing this program, I do not know what half adder looks like internally. Abstraction, right? I'm using half adder as a black box. I'm using half adder the same way until now as I was using a gate. Right? So until now I could use and, or, not, exclusive or, right? But now I'm saying, half adder, I'm telling you these are the inputs, this is the output. It's another box. And full adder is nothing but connection of boxes. This is the running theme in combinational circuits. Any combinational circuit is going to be a combination, wiring of these boxes. There is some restriction on this wiring. You can't create a cycle. And in fact, inadvertently, if you create a cycle, you take the output and wire it to its input, compiler will come back and say, sorry, you can't do that. There's a cycle here. And at that point, you'll say, boy, am I glad, I have types. Right? Because it's going to catch many mistakes of that sort in your thing. So this is my full adder using half adders. Okay, and we want to build a 2-bit triple carry adder. So I want to cascade 2 of them. Can you write this circuit, which I'm calling add 2, because it adds 2-bit numbers. And so what is the first input? A is how big? 2 bits. B is 2 bits, and the result is going to be 3 bits, right? 2 bits plus 1 for carry bit. Can you write down this function? Now we're going to use the full adder as an abstract thing. We just have to wire it up, right? And the wiring is already shown to you what you have to do, right? So you can just first declare S and C. So notice that S is going to be, the sum bits are going to be 2 bits. This is the blue spec notation for it. You are specifying the size by, in that constant, you're writing 2. And then B says it's binary, right? And furthermore, it's saying these bits are 0, 0. So the way to read this is that S has 2 wires. Initially, each S wire is 0. Yes? This is the declaration, right? I'm saying, I'm defining for you and giving initial value to this stuff. And C0, C has 3 bits in it, right? As the constant specifies, we have initialized it to 0, 0, 0. And we are saying C0 is 0. So this is a repetition of what is written over there. Okay, so I take the 3 bits and I apply full adder to it. Tell me if this makes sense. What is the input to this? X0, Y0, and C0. And what does it return? It returns a sum bit and a carry bit, which is shown here. Now remember that the 2 bits that we can extract it, so we can say some bit is the first bit of CS0, 0th bit of C0, and the carry bit is the first bit of the CS0. That's what is written in these lines over there. Okay, where A0, S0 is updated at this point, right? So other wires may be whatever they are, but this one is going to be wired connected to CS0 from now on. All right, and you are applying the full adder again, feeding it the right thing and extracting things from it. Wire S1 is updated. So first you updated wire S0, which is what we expect because we have 2 bits coming out. So one some bit is being updated here, second bit is being updated here, and we are carrying the results. And in the last case, what we have to return is C2 and S. How big is S? We had declared it to be 2 bits, right? So notice here that I could have written it explicitly. I could have said, oh, what I'm returning is C2, S1 and S0, because I have to return 3 bits. So this is all just convenience, right? That I know S is 2 bits, so I could have returned it like that. I can just return but if you return C, S, that will be wrong. How big is C? 3 bits, right? And which bit is being returned from C? Only carry out, the last one, right? So it's very, very important that that should say C2 over there. Okay, so that's what we have, cascading full adders. Now let me do selectors and multiplexers, which are also extremely useful circuits for us. Now, all of you at some level know the concept of a selector. I have, say, a 4-bit quantity, 4-bit vector, x0, x1, x2, x3, and I'm saying, give me the second one from it. So this is just simply a hardware connection. There is no hardware generated in this. So if you tell me that you want the second one, I just take that wire and connect it over there. So fixed selectors involve no hardware. It's just renaming the wire. That wire that was calling x2, from now on we can just call it whatever we want, right? We can say t equals x2, so t will be connected to that second wire of x. The problem is different if the value of I is dynamic. I want to build a general circuit which will, given I, will select the right wire from here and pass its value on. In other words, if we have 4 possibilities here, the value of I may be 0, 1, 2, 3, and depending upon what value of I you give me, that is the output I want. And whenever you have dynamic selection, this is a very famous hardware picture that you will see. It's called a MUX, a multiplexer, right? So it has 4 inputs coming in and a selector coming in, and depending upon the value of the selector, the output line will be connected to the input line. Important to understand that if you know the value of I, there is no circuit, you just directly connect it. But if you're going to know the value of I only when the circuit is executing, then you have to provide some hardware to achieve that effect. Okay, so let's see how we'll build a 2-way MUX, right? So I have 2 values, A and B, and I want to select them based on some predicate P, some Boolean value P in this. In BlueSpec, you can write it just like this. You can just say it's an expression, if the value of P is true, then produce A, otherwise produce B. So this is just an expression. You could have written it in Python also in this manner. Depending upon the value of the predicate, either it produces A or it produces B over there. Now, what is the hardware realization of this? Does this circuit make sense? What's happening in this circuit? You are saying my output will be A if P is false. My output will be B if P is true. And these are mutually exclusive, right? Either P is true or it's false. So when you merge them, that OR will only have one of the lines which corresponds to the input in this. So this is a very, very, you can write down the Boolean expression, for it. But there is a funny thing that we have to understand. We made a funny transition here from Booleans to, true and false. Because whenever you have if expressions, conditionals of any sort, you're saying if true, do this. If false, do this. So what is hard-coded here is any time you see true, it's going to be treated as bit 1. Anytime you see false, it's going to be treated as bit 0. Right? So that's very important. That's encoding of this thing. Now the interesting part of this circuit is, suppose the value of A is 32 bits. Suppose the value of B is 32 bits. But I still have 1-bit selector, picking between them. So how big is this circuit? What will this circuit look like? How many gates will you have?
Really quick, Arvind, I think the picture of the gate and the blue spec are flipped. So if P is true, then it should.
Oh, you're right, because corresponding to the expression I wrote, P question mark A colon B. Sorry, I should have. The mistake here is, how can I show this? This circle should be here, not here. Because when P is true, the value is A. When P is false, the value is B, according to this expression. Yes? Okay. Quickly, so how big is this circuit? I need this for every bit, right? Every bit of input. So if my inputs were 32 bits wide, the circuit has to be repeated 32 times. But the same predicate is being distributed. It's controlling all of them, right? So the input is only 1 bit, but it's connected to all 32 of them. And you will get used to this after a while. Something that may cost nothing. I mean, for you, if P, then A as B, you never think of the size of A and B. Believe me, in hardware, the cost is directly proportional to the size of A and B. So if you have gigantic A and Bs, these conditionals can be very expensive because they're going to take a lot of space, right? There is going to be lots of gates. And this is a strong enough circuit that I can easily build a 4-way multiplexer. Now, I could have written it as a case statement over here, that if I have 2 bits, S1 and S0, and I'm comparing them to 0, 0, 0, 1, 1, 0, and 1, 1, and I'm specifying the output in every case. This is the same thing as if I'm connecting these multiplexers in this manner. And you could have thought of this in terms of a procedure, a Python procedure that does the same thing. So I hope it's clear to everyone, and we'll explore this more in the recitation tomorrow, that given this simple multiplexer, 2-way multiplexer, you can build as big a multiplexer as you want, from it. So this is, even though I'm writing it like this, it should be obvious that I have 2 bits coming in, S0 and S1, and they're being compared against 2 constants over here. That's what is spelled out over here. And because of our convention that true always is 1 and false is always 0, I could have reduced it to simply not S1 and S2. And the n-way mux can be built using n-1 of these things. Good. In next lecture, I'm going to show you why we want to worry about gates, different types of gates. How much difference it's going to make in the size of circuits or speed of circuits using different kinds of gates in them. Thank you.